Welcome to my class. Today I'm going to explain backtracking basic method, and I will explain what first example, that is N-Queen's problem. So what is backtracking? So generally by using backtracking we can solve the problems which we can also solve in greedy method and dynamic programming. Okay, so in backtracking, generally which was coined by Lehmer. Okay, so backtracking method produces the desired solutions. Here also we show the desired solutions in terms of n tuples like dynamic programming. In dynamic programming also we represented all the solutions of the problems in terms of x1 to xn. Suppose if you see 0 R1 knapsack problem, we represent all the solutions in terms of x1 to xn. Here also the desired solution can be represented in terms of n tuples x1 to xn, and each xi we can choose from some finite set of items. Okay, so here while selecting the items, the criteria function must be satisfied. I mean constraints. Some constraints must be satisfied. Based on those constraints only, we can construct the solution. Okay, so here we need to apply sequence of trials. Okay, so after applying sequence of trials, if you decide that we can get the solution by going that particular path, then only we apply the remaining trials. Suppose if you want to solve any problem, but that problem is requiring n trials, up to this moment you have applied I trials. Let us assume I trials. Okay, so after applying I trials, if you see that there is no solution, even if you go further, there is no optimal solution we get, then we stop here and we come back to the previous position and we apply remaining trials, because instead of applying all the remaining trials from I plus 1 to n, because that is waste of time. Applying I plus 1 to n is waste of time, because we at this moment itself we decided that there is no solution we can obtain. So that's why by using backtracking concept we can backtrack, we can come back to previous state and we can apply the remaining choices. Okay, so that is called as backtracking. Even you see the procedure, suppose see you are there at kth element or kth element selection or kth solution construction. Up to this moment, we applied x of 1 to x of k minus 1. Suppose this kth solution is also belonging to the previously applied trial related solutions. And see here, this is bounding function. Okay, now. So b of x of 1 to x of k is not equal to 0 means if bounding function is true, then we need to verify whether x of 1 to x of k is leading to path or answer node. Suppose if x of k is the answer node, means this particular path is leading to answer node, then we immediately say that this is the answer. Then display x of 1 to x of k is the answer. Otherwise, if k is still less than n, because our target is to calculate the n element solutions or n solutions, still k is less than n, then apply the same procedure at k plus 1. Go to next element selection and apply same backtracking procedure, and again try to include that particular k plus 1 here. So up to x of k, if x of k plus 1 is belonging to x of k, means this particular family, then apply bounding function. If bounding function is also true, suppose if x of 1 to x of k plus 1 is leading to answer node, then display x of 1 to x of k plus 1. Otherwise, if k plus 1 is less than n, then go to next trial or next element and so on. So this is the backtracking procedure. Okay, now. So if you apply this procedure just with a slight modification, we can write other problems related algorithms. Okay, now this is the general method of backtracking. So by using this backtracking, we can solve some problems. Here, the one problem is N-Queen's problem. N-Queen's problem. So the problem aim is arrange all the given N-Queens, one queen at each row, and no queen should be attacking with no other queen. So means attacking means here no two queens should be there in same row, same column, and same diagonal. So here we are using one square box. Okay, or we can call it as a chess box, a chess board. Okay, we use chess board or n by n chess board or n by n square board, and we need to arrange all the queens in non-attackable locations. That to arrange each queen at each row. Okay, na? So here I am replacing n with 4, means 4 queens problem. So what do you mean by 4 queens problem? Arrange all the 4 queens in non-attackable locations, and each queen should be placed at each row, individual rows, unique rows. First queen should be placed at first row, second queen should be placed at second row, third queen should be placed at third row, and fourth queen should be placed at fourth row in non-attackable column numbers and diagonals. Because non-attackables means the constraint is No two queues should be there in same row, same column, and same diagonal. So that is the condition for arranging all the queues. See here. So this is called as state space tree or solution space. What do you mean by state space tree? Here state space tree is nothing but the tree structure format which shows all the possibilities of placing the queues. Okay, now, but we cannot say all these possibilities are leading to solution. Just here we are representing that these are the possibilities for placing the queues. Suppose you are there at root node. Okay, na? So that means here we are trying to place first queue on chessboard or square board, 4 by 4 chessboard or 4 by 4 square board. Here I am applying constraint as each queue should be placed in different rows. Okay, na? That to different columns also I am applying. Suppose first queue, if you try to place first queue means no other queue is there on chessboard or square board. Then first queue has 4 choices. We can place first queue in first column. Here solutions are column numbers. First queue can be placed in first column, or first queue can be placed in second column, or third column, or fourth column. So first queue has 4 choices. Suppose if we place first queue in first column, then for second queue 2, 3, 4 column numbers are possible. So here X is lower subscript is also representing row number. So this lower subscript of X is representing queue number as well as row number, and equal right side number is representing column number. Okay, na? So if you place first queue in first column, then what about column numbers for second queue? 2 or 3 or 4. Suppose if you place first queue in second column, then column numbers possible are 1 or 3 or 4, like this. Okay, na? 3 means 1 to 4 are remaining column numbers for second queue. 4 means now 1, 2, 3 are remaining column numbers for second queue. So like that, once you place first queue in first column, second queue in second column, then 3 and 4 are possible column numbers for placing third queue. And if you place 1, 2, 3, then 4 is column number for placing fourth queue. Like that, construct a tree completely with empty nodes. So after constructing tree with empty nodes by assigning edge values with column numbers like this, now give node numbers in 2 different ways. We can give node number in either breadth first search order or depth first search order. So depth first search order means just first start at root node and expand root node as its child. Once new node is visited, new node is reached, then temporarily the exploration of the node, selected node is stopped. That is depth first. In breadth first, once you select any node, that node must be explored completely. Then only we can explore next node. Here we are using queue as data structure for placing newly visited nodes. So one must be explored as 2, 3, 4, 5. So in depth first search, you must give the node numbers from top to bottom, that to left to right. So give this node number as 1 and left to right, start left to right from the next number. So 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Like that, we can give the node numbers from left to right, top to bottom in breadth first search. But in depth first search, once you reach new node, temporarily the exploration of the selected node is stopped. Now select this node for exploration. Once this node is reached, this node is expanded as new node, then temporarily the node exploration stopped here. Again expand this node like this. So 1, 2, 3, 4, 5. Again go back to 3 and explore it. 6, 7, 8, 9, 10. Okay, na? Then go back to this and 11, 12. So like this, if you give the node numbers, then that particular node number is called as depth first search node number. So, but whatever the node number format or order you give, you can give it either breadth first search order or depth first search order. So like this, we can construct a state space tree or solution space. Now this tree structure is called as state space tree. Now our ultimate target is construct the solution now. Okay, na? So at least construct first solution and involve the nodes wherever the node inclusion possible. Go up to that and apply bounding function every time. Our bounding function means we need to apply constraint or criteria whether new queue, whatever the new queue placed in current column, whether that queue is attacking with any other queue which is already placed on chessboard or square board, we need to check. Okay, now suppose if that queue is attacking, then no need to apply these trials, because here itself, suppose if you place first queue in first column, second queue in second column, both are there in same diagonal, then no need to search these possibilities. Okay, after applying this trial, we failed because this is not leading to solution. Then here itself we can cut the search procedure. Then go back to this and try to place second queue in third column. Then up to this is safe. But if you try to place second queen, third queen in second column, 2 and 3 both are attacking each other, then no need to search this. And other alternatives, if you place first queen in first column, second queen in third column, then one possibility is for third queen in second column, but both are attacking each other. And another possibility is fourth column. Again, 3 and 4 are attacking each other. So like that, we need to search the solution on state space tree or solution space. Okay, after searching the state space tree or solution space, we get the solution like this. This is the solution. Okay, whatever the nodes you visited while constructing solution, you must include those nodes in the solution space. So this is solution. This tree is called solution space tree. Earlier tree is solution space. This is solution space or state space tree. And this tree is solution because I will tell you. Suppose if you place first queen in first column, if you try to place second queen in second column, both are attacking each other. Here itself, there is no possibility of getting solution. Then what is the necessity of searching this entire tree? So that's why we represented that particular node with P means bounding function is failed. Then take backtrack here. Then go back to this and try to place second queen in third column. So first queen is there in first column, second queen is there in third column. I will show you in by using matrix also. Okay, na? But this is tree structure. We are tracing previous state space tree or solution space. So up to this is safe. But if you try to place third queen in second column, these two are attacking each other. Then there is no solution in this path. If you try to place third queen in fourth column, these two are attacking each other. Then there is no solution in this path. Then go back to this and apply another alternate. Another alternate is fourth column. So 1 and 4 both are safe. But if you try to place second column, this is safe. But fourth queen, this is attacking. Here also third queen, these two are attacking. So placing first queen at first column is not producing solution. Then place first queen at second column. Then 1, 2, both are attacking each other. 1, 3, both are attacking each other. Then only one possibility is there for second queen, that is fourth column. Okay, na? After placing second queen in fourth column, then third queen has 1 and 3. Then select first one. 1, yeah, 1 is okay. So 1 is not attacking. Then 2, 4, 1 are over, then 3. Okay, na? So this is the solution node. 31 is solution node. What is solution path? 1, 18, 29, 30, 31 is solution path. Then what is the solution now? X1 equal to 2 is first queen solution. X2 equal to 4 is second queen solution. X3 equal to 1 is third queen solution. X4 equal to 3 is fourth queen solution. So our target is first to say what is the solution node in state space tree. Solution node is 31. Then what is the solution path in state space tree or solution space? Path is from root node or at least from leaf for the selected node, you can trace back. So 31 to 30, 30 to 29, 29 to 18, 18 to 1. Up to reaching root node, we must trace back, okay, from the current node, means solution node, up to root node. So this is giving solution path. So 1, 18, 29, 30, 31 is solution path. Solution node is 31. And solution is first queen should be placed in second column and second queen is placed in fourth column. Third queen is placed in first column and fourth queen is placed in third column. Then only we get answer. I will show you by using square box or chessboard. This same solution I will show you in square box or chessboard. Wherever placement is not possible or wherever tracing is, or wherever further searching is not possible, simply represent that node with P. Means we are cutting the search process. We are stopping search process. We are killing all the remaining nodes in the solution tree and trace back to previous node. Okay, come back to previous node. This B means bounding function is failed. Then take backtrack to previous node and search other alternates. Okay, now see this. Now take the 4x4 chessboard or square board and place first queen in first column because no other queen is there. Then try to place second queen. Here we are trying to place anywhere. No need to check this because in our procedure we are not placing queen in same column. Of course, even you try to place, these two are attacking. Here also these two are there in same diagonal because the stars are representing tried but failed. Stars are representing tried to place the concerned queue but failed. Up to this is okay. This column queen is this position third column is for the second queen is okay. But while trying to place third queen, if you try to place queen here, these two are attacking because both are there in same column. If you try to place here, these two are attacking each other because both are there in same diagonal. So these two are there in same column. These two are there in same diagonal. So third queen placement is not possible if first queen is there at first column and second queen is there at third column. Then what will we do? Then go back to previous queen position and change queen location to next column. next column means q2 must be placed in second column. Now try to place third queue. Third queue, if you try to place first column, both are attacking each other, then this is the safest place up to this moment. But while trying to place fourth queue, here if you try to place fourth queue, q1 and this queue are attacking each other. Here q3 and this queue are attacking each other. Here q3 and this queue are attacking each other. Here q2 and this queue are attacking each other. No placement is possible. Then go to previous queue and try to move this queue to here. Both are attacking each other. Try to move this queue here. Both are attacking each other. There is no other alternate. Then go back to queue 2. Then there is no other alternate for moving. Then go back to first row and change first queue to second column. Now try to place second queue. Here not possible. Both are there in same diagonal. Here both are there in same column. Here both are there in same diagonal. Then only fourth column is possible. I have shown only fourth column is, if you place first queue at second column and second should be placed at fourth column. Okay na? Then what about third queue? Here this place is safest because this is not attacking with any other queue which is already placed. Then try to place fourth queue. Here not possible. Here both are attacking. Here possible. So 1 4 2 4 1 3 are solutions. 2 4 1 3 are solutions. So this is fourth queue, four queues problem solution. Okay, now this is state space tree of four queues problem, and this is the solution construction of four queues problem. So based on this only we are constructing solution tree. So based on this we are tracing the state space tree. Based on these moves we are cutting some search procedures. Okay, now 1 2, then 3 is not possible because tried and failed. Then we construct a solution tree from the state space tree by using these moves. These moves are applied on state space tree, and finally we constructed this tree is the solution tree from the state space tree. So we can generalize this to 8 queues or any other queues. If we replace n with 4, then we get a 4 queues problem. Then we can solve 4 queues problem like this. If we replace n with 8, then we get 8 queues problem. Okay, na? Then generalize this as n queues problem. But in n queues, just by seeing this diagram, we can say both are there in same row, same column, or same diagonal. But how can we say in n queues problem, how can we say both are there in same diagonal? Because diagonal is difficult. Of course, same row or same column means if you extract two queues, row number and column numbers. Suppose first queue row number is row number column numbers are I and j. If second queue row and column numbers are k and l. So first queue row number is I, second queue row number is k. If both are same, then we say that both are there in same row. Suppose first queue column number is j, second queue column number is l. Because those are appearing outside, those are appearing explicitly. Because if you extract or if you collect two queues, row number and column numbers, then explicitly row number and column number are visible. Then by seeing those row numbers of two queues, row or column numbers of two queues, we say that both are there in same row or same column. But what will happen? How can you say whether both are there in same diagonal or not? It will little complex compared to row numbers and column numbers. Very simple equation is there. We say that there are two different diagonals. One is left diagonal, means starts at topmost left corner and end at rightmost bottom corner. Or here if one queue is there here, another queue is there here, this is right diagonal, left to right diagonal. Even one queue is there here and another queue is there here, this is right to left diagonal. Okay, na? What about left to right diagonal? What about right to left diagonal? If your diagonal starts at rightmost rightmost top corner and ends at the leftmost bottom corner, then that particular diagonal is called right diagonal. So here suppose one queue is there here, another queue is there here. So these two queues are there in right diagonal, and these two queues are there in right diagonal. These two queues are there in right diagonal. These two queues are there in left diagonal, and these three queues are there in left diagonal. So like that we can recognize. But how can we say both are there in same diagonal or not? Very simple equation is there. By using that equation, we can say that both are there in same diagonal or not. See, suppose if left diagonal, what is left diagonal? If left diagonal is started at upper left corner and ends at lower right corner, then if any two queues are there in that particular diagonal locations, then those two queues rows and column numbers are same. Row minus column number is same. Suppose right diagonal, if one queue is there at the right top right, and another queue is there below it, but both are there in same diagonal, like I explained earlier, then row plus column number should be equal. I took one example, don't worry. If if any two queues are there in left diagonal, okay na, then row minus column number should be same. If two queues are there in right diagonal, then row plus column number should be same. First one is row minus column number. So first second one is row plus column number. So calculate row minus column value of first queue and second queue. If both are same, we say that both are there in same diagonal. Or if we calculate row plus column number of both the queues, if both are same, then we say that both are there in same diagonal. So like that, I took one example here. Suppose if one queue is there in ith row jth column, another queue is there in kth row lth column. So what is first diagonal with respect to first diagonal? Row minus column number should be equal. I minus j equal to k minus l. I minus j equal to k minus l. Then bring column numbers one side and row numbers one side. If you bring column numbers one side, then j minus l equal to I minus k. Bring k here and j this side. And what about according to second diagonal? Row plus column number should be equal. So row plus column I plus j equal to k plus l. So like that, same story. Bring column numbers one side or row numbers one side. So what is the difference in these two? Only negative sign is different because j minus l, here also j minus l. Here I minus k is there, here k minus I is there. Okay, na? So negative is different. So that's why take mod of column numbers difference equal to mod of row numbers difference. Mod of column numbers difference equal to mod of row numbers difference of those two queues. Then we say that both are there in same diagonal. So take two queues row number and column numbers, and say calculate columns difference and row numbers difference. If both are same, irrespective of the sign, if both the magnitudes are same, or the numbers are same, differences are same, then we say that both are there in same diagonal. So like that, how can you say both are there in same row? If I equal to k, then both are there in same row. If j equal to l, both are there in same column. So by seeing those row number and column numbers of both the queues, we say that both are there in same row or same diagonal. Just by calculating row numbers difference and column numbers difference, if both the values are same, irrespective of the negative sign value, then we say that both are there in same diagonal. So like that, we can recognize whether two queues are there in same row, same column, or same diagonal. So based on that, we say that both are attacking each other or not, or any queue is attacking with any other queue which is already placed in queue chessboard or not. We can easily identify based on these three principles. Okay. Now this is the procedure for n-queues problem. Here we are trying to place the kth queue in n by n chessboard. Now try to extract all the placed queues. So we need to find appropriate placement for kth queue. Okay, na appropriate placement for kth queue by checking all the column numbers. Okay, so place of k minus I. So this place of k minus I is the separate function we are calling here, which finds whether ith column number is appropriate location for kth queue or not. So simply place of k minus 1 is simply writing so answer as true or false. If it is true, then we say that this column number is appropriate for placing k. Suppose if column number is appropriate, then we say that this column number is appropriate for kth queue, then x of k equal to I. If k equal to n, then that is the last queue to be placed. Then we simply write x of 1 to x of n is the solution. Otherwise, we need to place next queue in n by n chessboard. Next queue is k plus 1. Okay, na? Then what is place now? So this place is the procedure which is used for finding appropriate column number for kth queue. Now try to extract all the already placed queue column numbers. Already placed queues are 1 to k minus 1. Okay, na? Take one loop. Okay, na? To extract column numbers. If x of j equal to I, okay, na? I is column number of kth queue. Here this is say j. This is j. Sorry, this is j. For j equal to 1 to k minus 1. If x of j equal to I, what is x of j? Column number of jth queue already placed is equal to column number of k. Then simply write column numbers are same. Okay, na? Or I told you na, row numbers difference and column numbers difference. Calculate row numbers difference and column numbers difference. If row numbers and column numbers difference, so both are same, then write false. Then go to next column, next queue number, and so on, or column numbers. So select all the column numbers, first column, second column, third column, fourth column, and so on. So up to nth column. So start at first column, try to place kth queue in kth row first column, kth row second column, because each queue can be placed in different rows. So kth queue must be placed in kth row. Just by checking all the column numbers here, we need to identify which column number is appropriate column number for placing kth queue in kth row. That's why we called place as a procedure. So this place procedure is this. Now take for j equal to 1 to k minus 1, because I is already there, then take j here. For j equal to 1 to k minus 1, we placed k minus 1 queues in chessboard already. Now we are trying to place kth queue at ith column. Then check all the queue, already placed the queue number, queues column number with column number I. If column numbers are same, or row number difference and column number difference both are same, then write false. If it is false, then I will be incremented by 1 unit, and we need to check I by I at 2, 3, 4, 5, and so on. So in this way, we can find appropriate placement for kth queue. And after placing kth queue in appropriate location, we are trying to place k plus 1th queue by calling the same procedure. Again, this procedure again calling place as a procedure, which verifies all the column numbers from 1 to n. Okay, which which finds appropriate column number for placing k plus 1, and so on. So we need to repeat this procedure until placing all the queues in n by n chessboard or n by n square board. So in this way, we can calculate appropriate column numbers for n queues. Okay, na? Solutions are x of 1, x of 2, so on, x of n only. Okay, na? Now, so this is the number of nodes. How many number of nodes that are possible, or how many number of 8 tuples we need to examine, because x of 1 to x of 8 are the required solutions. X of 1 to x of 8. Okay, all the leaf nodes in 8 by 8 chessboard, because if you construct a state space tree, then state space tree is containing 8 levels, and the last level, because each level, if you trace from root node to each leaf node, then we observe x of 1 to x of 8. Each leaf node is, if we trace from leaf node to root node, x of 1 to x of 8 we can. Okay, na? Even it's trace from node number 5 to 1, node number 7 to 1, node number 10 to 1, x of 1 to x of 4 are there. Like that, if you extend this particular tree structure to 8 queues problem, we get leaf nodes here. Okay, if we trace back from leaf node to root node, which produces x of 1 to x of 8, but all those tuples are not leading to solutions. Okay, na? Some attackable locations are also there. But how many 8 tuples we need to examine, we will see. Suppose if we take 8 by 8 chessboard or square board, then how many possible ways to place 8 queues without applying any condition? 64C8. 64C8, because number of boxes are 64. We are trying to place 8 queues in 64 boxes. In this number of possible ways we can place, but some attackable locations are also there. So approximately that number is becoming 4.4 billion 8 tuples we need to examine. But if we apply distinct rows and distinct columns related conditions, only 8 factorial, at most 8 factorial number of 8 tuples we need to examine. So that 8 factorial is equal to 40,320. Then how many number of nodes that are there in state space tree? See, this is the number of nodes in state space tree, because initially this is root node, and root node is containing eight children. Those it's because j equal to 0 to 7 we are supposed to start. So initially first column is I equal to 0 to j. So I equal to 0 means 8 minus 0. So root node is containing 8 children. Okay, na? And again each child is containing 7 children. Each that particular level, each child is containing 6 children, and so on. So finally the last but one nodes are containing only one child, like this. Okay, na? Here the root node is containing 4 children, and again each child of the root node is containing 3 children, and each child of this is containing 2 children, and so on. Okay, na? From root node to leaf node, the number of children are reducing, because initially all the columns are possible for first queue. If you place first queue in one particular column, and the remaining column numbers are possible for second queue, and so on, like that 8 queues also. Okay, na? So that's why the number of column numbers are decreasing. 8 minus 0 is the first level, 8 minus 2 is the second level, 8 minus 3 is the third level, and so on. So like that, if we construct by imposing the conditions, then 69,281 nodes are there that are required to construct state space tree. So in this way, we can calculate the number of nodes required to construct state space tree. Okay, na? But out of these, only 2.34% number of nodes are there for state space tree, that are number of possible nodes. Okay, na? That are only about to estimate are unbounded nodes. Only 2.34% are unbounded nodes. The remaining nodes are bounded, means function is constraint is paid. We need to take back from that particular node, like this. Okay, na? Constraint is paid.
only 2.34% nodes are unbounded nodes. These are bounded. So these are bounded. Unbounded means whatever the nodes that are represented in solution tree. So those are unbounded, and rest of the nodes are bounded nodes. So these are bounded nodes. Whatever the nodes that are appearing in this particular state solution tree, but which are there in state space tree or solution space, are bounded nodes. So these are unbounded nodes. Okay, na? So like this, we can construct a solution for HQ's problem. Okay, na? So thank you for watching my video. Thank you.